So here we go. Almost done. For the year, almost done. We talked about neutralization reactions yesterday. Not yesterday, Friday. And hopefully that made sense, that just the writing the equations. Now just a quick reminder here. When you add an acid and a base together, what are the two things that get produced? Just kind of... Okay, water is one. And some sort of salt, which just means an ionic compound of some sort. Okay? So it forms, the H plus and the OH minus form water. And then whatever was connected to the H plus and the OH minus come together and form some sort of ionic compound. And that's it. Okay? So hopefully those are pretty easy. Now let's talk about titrations. Okay? Titration involves adding an acid and a base together. Now, well, okay, I say that. You can do other types of titrations besides acid-base titrations. We're going to focus on acid-base titrations right now. Okay? So any titration, just titrations in general, can be used to determine the unknown concentrations of solutions. So let's say you've got a solution, you know what it is, but you don't know how concentrated it is. This is actually a technique you can use to figure that out. Okay. So titrations, again, sorry, get back where we were here. Start with, you're going to need something that has a known concentration that will react with it. All right, so what we're going to use is something that we know the concentration of. We're going to add that to our unknown, and then based on how much we have to add, we can figure out what the concentration of our unknown actually is. Then we're going to construct something called the titration curve. Okay, you guys are going to get practice with this tomorrow. You're going to add measured volumes of known concentration to the unknown, and then you're going to take the pH and graph it. Okay. Now what we may do, we may not mess with the pH meters this year. That's technically how it's, really supposed to be done. But you can also do a titration using indicators, where you're basically just adding a certain amount of base to acid until the acid starts to turn pink, because we've added an indicator into it. So I think that's probably what we'll do for our practice titrations, just because we don't have a lot of time left. And doing it with the pH meters takes a while. Now you will, if you go on to AP Chemistry, you will be using the pH meters, and you will make graphs of your titration curves. And I'll show you what that looks like, okay? But I don't think we need to worry about that for the end of the year here. So you're going to analyze the titration curve, and then we're going to look at one. All right, so here's the idea. And again, not all of this needs to make sense to you right now. But basically, what we usually do when we do a titration is we start with the acid. Now, you don't have to do that, but that's typically the way it's done. All right? So look, if you look at this graph, just kind of reading what this graph is telling you, this is pH on the left side of this graph, right? So pH of about 2.1 maybe to start with. So what kind of solution are we dealing with here? It has a pH of 2.1 to start with. That's an acid, right? Okay. So, and we could just tell because it's a very low pH. So we are adding a base into an acid. Now, how do I know that I'm adding base as we go along here? Yeah. I mean, the only way that we could make the pH get higher is to add a base to that solution, right? Because that's going to make the pH go up. So we've got an acid here. We're adding a base to it, okay? So what happens here is as you add the base, the pH starts to go up for a little while. And then once you get to the equivalence point, it really shoots up, okay? And now this is going to be the most frustrating thing for you guys about a titration. You can add 1 or 2 drops too many, and your solution will turn dark pink, all right? What you're shooting for, yeah, and some of you have done. So you want a really light pink because that means your pH is probably right about here, okay? If you add too much, then you're up here, and that's too much, okay? But again, we'll get to all of that. But the idea here is you add base to the acid. It's going to stay a low pH for a while, and then all of a sudden it's going to shoot up, Okay, and then you're going to have a really high pH. And this down here is just the volume of base added. I guess that's the other way you can tell that it's a base you're adding, is because it says you're adding a base. Do you guys have this graph on your notes? Okay, so you have that to look at. That's good. That's what a titration curve basically looks like. Okay? All right. So now we need to do actual calculations. Okay? So you want to find the equivalence point. The equivalence point is in the middle of the big jump. And that represents where you've added as much acid as you had base, or added as much base as you had acid, just depending. Okay. So right about here, right about here in the middle, that's our equivalence point. You guys see that? It's in the middle of that really steep curve there. Okay. And the equivalence point, that's when we've added as many moles of base as the moles of acid that we had, okay? So you need to remember this. Moles of base equals moles of acid at the equivalence point. This is going to help you do the practice problems that we have to do in just a minute, okay? So at that point, the moles of OH minus that we've put into the solution should be equal to the moles of H plus that we started with. Now, when we add that OH minus to the H plus, what happens? What do they do? H plus plus OH minus gives me H2O. Turns into water, right? Does it make sense that when we have equal amounts of H plus and OH minus, the pH is 7? Does that make sense? Because the H plus and the OH minus have all reacted, and now we just have water. And the pH of pure water is 7. Okay? Now I'm cheating a little bit. There's some other things going on there, but that's the basic idea. Okay? When you add a strong acid to a strong base, the pH at the equivalence point is going to be 7 because the H plus and the OH minus all react with one another just to make water. Okay? All right, then we got to choose an indicator. An indicator is something that can be added to the solution to cause it to change color when a certain pH is reached. The indicator we're going to use in here is phenolphthalein. I'm not sure if it says that on here. And you do not need to know how to spell phenolphthalein. It's the weirdest word in the world. Here, I'll just show it to you. I don't think it's on your notes. It might be. Because let's put a pH and a TH together. That'll be a lot of fun, right? Phenolphthalein. It's just an awkward word. But that's what it is. That's the indicator that we normally use. That indicator is clear. It's colorless when it's in the presence of an acid. When the solution turns basic, it turns pink. All right? So that's what's going on with your titration. So we can actually choose this indicator, and it will show us right when the solution turns from acidic to basic. We can see that exact point because of the phenolphthalein indicator that we have in there. Okay? Now, this is not going to make a lot of sense to you. I need to just kind of show you a problem. So I wouldn't worry too much about this formula. I wouldn't use a formula for these. Yeah, I'm not even going to use a formula there. We'll just talk about how to do this, okay? So first step in any titration, you need to write the balanced chemical equation, okay? Because essentially what we're doing here, it's sort of like a stoichiometry problem, but it's a really, really, really easy stoichiometry problem, okay? It's basically the same every time. Then we're going to calculate the number of moles of the base or the acid in the volume of the standard solution that was added. And then we're going to say, okay, the mole ratio from our balanced chemical equation will help us to know how many moles of the unknown that we had, okay? And again, this is all just words. It's not going to make a lot of sense until we go through a practice problem. And you're going to use the molarity equation to calculate the unknown molarity. Okay, so here's an example. What is the concentration of sodium hydroxide if 28.0 milliliters is neutralized by 34.7 milliliters of 1.2 molar HNO3? Okay, what do we say step 1 is? Balanced chemical equation, okay? So we're reacting NaOH and HNO3, right? So what is going to be produced here? Remember how these reactions work? They're kind of like what? Double replacement or wife swap reactions, right? Okay. So the H goes with the OH, forms water. And then what's the other thing that gets formed here? What's left over? Yeah, the Na and the NO3, right? Sodium's a 1 plus. NO3, does anybody know what the charge on NO3 is? A 1 minus. If you don't know, you have your polyatomic ion chart. You can look it up. So 1 plus and a 1 minus, it's just going to be a 1-to-1 ratio. NaNO3. Okay? Is that equation balanced? Yeah, it actually is. So that's nice. We don't have to worry about coefficients here. Okay? Most of the titration reactions that we do will already be balanced. There are a couple exceptions to that, so you just have to be careful. All right, so we've got a balanced chemical equation. Okay? We're trying to figure out the molarity of NaOH. Okay? That's where we're trying to get to at the end, right? So molarity of NaOH, we'd need to know the moles of NaOH over the liters of solution, right? Does that make sense? So what we don't know at the moment, we know the volume of the NaOH solution originally, right? But we don't know the number of moles of NaOH we have in the solution. So that's why we're doing the titration in the first place, okay? So in order to neutralize this, neutralize means we reach the equivalence point. That's another way of saying that, okay? We need to add 34.7 milliliters of the 1.2 molar HNO3. Any ideas on what to do here? If I want to figure out how many moles of NaOH that I have, just think stoichiometry for a second here. If I figure out the number of moles of HNO3 that I have, could I then figure out the number of moles of NaOH that I have? You can just use the mole ratios in the equation, right? Okay. So if I can figure out how many moles of this I have, actually it's really easy in this one because it's a 1-to-1 ratio, right? So however many moles of HNO3 I have, that's how many moles of NaOH that I have. Does that make sense? So let's figure out how many moles of HNO3 that I have. Well, how do I do that? Molarity equals moles of HNO3 over liters of solution, right? We know this for the HNO3. We know the concentration, and we know the volume for the HNO3. So then we can figure out the number of moles if we plug those two things in, okay? So our molarity here is 1.2. That's equal to, we'll just call this X up here. Okay, that's what we're trying to find is the moles of HNO3. Divided by our liters of solution. Now, how many liters of solution do we have? That's how many milliliters of solution we have, right? Yeah, 0.0347. You have to divide that by 1,000 to get to liters, right? Now, here's where some of you really struggle with the algebra. If your x is on top of the equation, what do you do to solve for x? You multiply both sides by the 0.0347, right? Okay? I think it's easier. That's why I replaced this with an x instead of the moles of HNO3. I think it's easier to see if it's like this. Okay? So then when you do that, calculator here. That gives you 0.04164, but we're going to round that to, I guess, 0.042, right? And that's moles of HNO3, okay? So if we've got 0.042 moles of HNO3, this step is really kind of unnecessary, but I'm going to show it to you just so that you can see it. I'm going to go from moles of HNO3 to moles of NaOH, right? But this is just a 1-to-1 ratio because there's just ones in the equation. that's the coefficient in front of these formulas in the equation, right? Okay, so that's going to give me the number of moles of NaOH. It's the same. It's 0.042. Okay? So now that I have that, 0.042, I can plug that in up here. And I know the volume of my solution for my NaOH, right? That's going to give me my molarity. So it's going to be 0.042 moles divided by, and again, you have to change this to liters, so it's going to be 0.028 liters, 0.0280, I guess, liters. Okay? Now, this number, you probably don't want to round that until the very end. I just rounded it here because of space constraints. So I'm ending up with the number 1.48714, on and on. We need to round this to 2 sig figs, right? Why are we rounding it to 2 sig figs, ultimately? Which are the numbers in our problem here?
1.2.
Yeah, this one, 1.2 molar, that's only 2 sig figs, right? So we're going to end up with 1.5 is the concentration of our NaOH. Okay? So let me just kind of talk you through what we would have done in a lab setting to make this happen, okay? And again, I'll show you kind of how this works tomorrow. But usually what we do, if we want to do this, we've got 28 milliliters of the base sitting in a beaker, okay? We're going to add 1.2 molar nitric acid in a burette. You guys know what I mean when I say a burette? Remember what those are? They're the really tall, skinny things that measure. Actually, there's one right back there that Kristen's working on. So you can kind of see what the burette no, not that. That's the volumetric flask. There you go, the burette. So that's what the burette looks like. We'll be using those starting tomorrow, okay? But basically what you would do is you turn a little valve, and that would let the nitric acid start going into the beaker of sodium hydroxide. It would turn pink, a very, very light pink, right at 34.7 milliliters after you've added that much of the acid, okay? Then you do this calculation, and you figure out, okay, that original sodium hydroxide was 1.5 molar concentration. Now, is that the concentration of the sodium hydroxide in that solution anymore? Why would the concentration now be different? What else did we add besides nitric acid into that solution? What was mixed in with the nitric acid? Water? Was there water in there? Yeah, there's probably water in there, right? Because 1.2 molar means it's dissolved in water, okay? So we added some extra water to that solution, so it's not 1.5 molar anymore in your beaker, right? Actually, the other reason it's not 1.5 molar anymore is because all of that OH reacted with H+, and now it's just water, okay? But that was the original concentration of the sodium hydroxide before we started doing our titration, okay? Ooh, that's it. That's not a lot of practice, but that's basically what all the problems look like, okay? So I'm going to give you a couple of practice worksheets. I'm also going to post something on Moodle because this concept is a little tricky. It's actually a really good resource sheet, and basically what it does is it gives you several examples where it walks you step by step through the process like we just did, okay? And then it gives you some practice problems that you can try along with, I believe it gives you the answers for the practice problems. So that could be a good resource if you feel like you need some extra help on these, okay? We've got, how much time right now? We've got about 20 minutes right now, so I would definitely take use of that time and make sure that you're asking me questions in class after I give you the worksheets, okay? And then we'll have a quiz. First thing tomorrow, it'll be just a couple of questions. I want it to be nice and short. And then we'll start titrating tomorrow. I'll show you kind of how that works, okay? All right. Video is over.